Hello, it's Bill again, and thanks for joining us on this exploration of gravity. This discovery came as a result of my friend Alex asking an often dismissed question. That question was, what can be done with the energies in a quantum mechanical constrained degree of freedom? That question led to answers that led the way to gravity. My hope is that this video will allow everyone to embark on the same journey to the discovery of gravity and feel the awe-inspiring beauty of nature. So we begin with Maxwell's demon. Max is in a room full of gas, and there are particles with a range of speeds all moving in different directions. This activity averages into a temperature and pressure. Max tries to reduce entropy in the box so that all the hot particles are on the right side. He measures particles that happen by and opens the door only for hot particles. It seems he can separate hot from cold for free, and that seems to violate entropy. However, there is a cost to measurement, and that will create more heat on the left side. Then the left and the right side will equalize again, all because the cost of energy Max has to spend on the cool side of the box to perform a measurement. The price of measurement can be paid in the form of a photon or even in the form of a bit of gravity, as we soon shall see. So how to find the energy cost for measurement? How much does Maxwell's demon have to pay to measure spin of entangled particles on an event horizon 1 kilometer black hole? Now this will take a few steps. Step 1, find the total gravitational energy of that black hole and divide by the total number of Planck areas on the horizon to get a per Planck area of gravitational energy. Step 2, find the Hawking temperature of that given black hole. Step 3, find the amount of energy Maxwell's demon has to pay to measure the spin state of the particle by plugging in the Hawking temperature into the Landauer limit and report that value in joules. Check both values and see if the amount of energy Maxwell's demon has to pay, the Landauer limit energy, is the same value for the gravity bit. So first we're going to find the gravitational energy per Planck area. And we use the Schwarzschild metric, and we find that it's 6.735 times 10 to the 29 kilograms. We then use equals mc squared, calculate the total energy, which is 6.0736 times 10 to the 46 joules. Now we're going to take that entire energy value, 10 to the 46 joules, and we're going to divide it by the number of Planck areas on that black hole. And what we find is the gravity per Planck area from General Relativity is 1.261 times 10 to the negative 30 joules. Step 3, we're going to find the Landauer limit at Hawking temperature. So we're going to find out how much Maxwell's demon has to pay to measure entangled pair by finding the Hawking temperature. The Hawking temperature is the temperature black holes emit as entropy, and black holes are usually very cold. Then we enter the Hawking temperature into the Landauer limit equation. This will tell us how much energy is required to erase a given quantum bit, which is the same amount of energy contained within that quantum bit. You can think of entangled particles as quantum bits. We use Hawking temperature because it flattens all the kinetic energy of the particles interacting on a black hole event horizon surface. And it leaves only the value of the bit itself, which is the minimum energy needed to measure a particle's spin state. And what we find when we enter Hawking temperature into the Landauer limit formula is 1.74 times 10 to the negative 30 joules. Now we're going to compare the results to see if there's a connection. From GR, General Relativity, we got 1.261 times 10 to the negative 30 joules. We use the quantum mechanical way by using Landauer limit at Hawking temperature, we got 1.74 times 10 to the negative 30 joules. This is a difference factor of 0.724. This is looks like an emission process. It's actually very close to 1 divided by natural log 4, which indicates a 4-bit quantum system. But it looks like kind of like an emission process, and that's why Landauer is a little bit higher than the general relativity number. But now we have enough information so Maxwell's demon can go to the horizon and measure an actual entanglement in process and see how the magic happens. Max decided to measure the spin of entangled particles A and B. Now Max does not know the spin of either particle because the particles are in a superposition, both up and down spin states. And Max must perform a measurement to reveal the spin. Both A and B have a 50% chance for up and a 50% chance for down. And both A and B have up and down bits. There are 4 bits in a 2-bit system. The bits are up, down, 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 up, down, up. You can think of these bits almost like computer bits. 0 or a 1 is kind of like up or down. Because A and B are entangled, their revealed spin states must always be opposite. This means down, down, and up must be expended in some way. Before Max measures A, he looks at the matter particle closely and sees it has 720 degrees of spin information. Max realizes that when he measures A's spin, he will only see 360 degrees of that spin. And that means the remaining 360 degrees of unobserved spin information can't disappear. Max is about to find out where it went. Step 1. Max measures the spin of A and finds up. Because the particles were entangled, up, and down are forbidden. It's kind of like how meshed gears have to rotate in opposite directions. If you have one gear rotating clockwise, then the other must be turning counterclockwise. This is conservation of angular momentum. The unused portion of the particle's spin, the down in this case, turns into a wormhole-like object at 1.74 times 10 to the negative 30 joules. So A and B's spin will interact briefly. So their spin states will be opposite, just like the example of gears. So the down goes and creates this wormhole-like object so A can affect B. Max realizes that if he had measured A and found down instead of an up, then the unused portion of A's wave function would be the up portion, and that would become the wormhole-like object. It's always A's counterfactual, the opposite of the emerged state, that becomes the gravity bit. Max sees it's not really a wormhole, not quite a tunnel. Still can't figure it out yet, but Max will get to the bottom of this mystery. The wormhole energy only exists long enough for A's spin to affect B's spin, and then it's gone. The energy from that wormhole-like object spreads like an expanding bubble and is what causes gravity at the energy level of 1.74 times 10 to the negative 30 joules per entanglement. Now Max wants to make sure he got his money's worth. He was told entanglement always shows opposite results, no matter which particle's measured first. Max measures the second particle of the pair B and finds down. And then B's unused up portion is emitted as a Hawking photon at Max's energy cost of 1.74 times 10 to the negative 30 joules, the same energy as the wormhole-like object was. Now this time Max is at a 100 kilometer radius black hole, and he wants to see how things work there. For one thing, he notices that larger black holes have a lower Hawking temperature, and therefore a lower cost for Max to measure. Max is excited. It costs him 1/100th of the amount of energy to do the exact same kind of measurement as he was doing on the 1 kilometer black hole. So we can see here that instead of 1.74 times 10 to the negative 30 joules, we're coming up with to the negative 32 joules. Now this is the static Landauer limit, and then general relativity would record that value at 1.261 times 10 to the negative 32 joules per entanglement. So we see that Landauer scales with radius. Max realized something. Even if particles A and B are light years apart, they can still correlate their spins instantly. How does this happen? Max saw that the wormholes weren't really tunnels. Max has heard that there is a distant holographic particle horizon that may contain the reason why. Now Max has to play sleuth and look for something that might aid in the translation of particle spin information across vast distances. Some structure that may allow instant causal contact between entangled particles in spite of being billions of light years apart in 3D space. Something about the way holograms work seems to point to an answer. Max had to look all the way to the cosmic event horizon where all particles are sort of smeared holographically, encoded is a better word, equally across the entire horizon. Max can see pieces of A and B everywhere on that horizon in a holographic format. Particles A and B are encoded equally over that entire 2D spherical area of the horizon, billions of light years away. Even if particles A and B are billions of light years apart in 3D space, on the cosmic holographic horizon, all particles are actually right next to each other. They're adjacent. A and B are entangled and share a common wave function, which you can think of sort of as an address, where you can find particles A and B in holographic space. So you can see that parts of A and B are all over, smeared over this entire holographic horizon, 13.8 billion light years away, and the spins are all smeared kind of all over this entire horizon. If you could look at a piece of the holographic structure of a particle on the horizon, up very close, it would look similar to how a hologram looks under a microscope. It's complicated, looks almost random, and not representative of the image you see at a distance. Holograms encode 3D information onto a 2D surface, with every element in 3D space being encoded everywhere across that surface in a 2D holographic format. This is why you can cut a hologram in half and get two identical full images, but at lower resolution. Entangled pair A and B are encoded in a similar way as the objects in a hologram are encoded. It's the relations between holographic elements that causes objects to emerge in 3D space. The holographic horizon gravitates things out of the observable universe, and it's the size it is from all the objects that have crossed the horizon and left their departure energy. It was captured on that horizon and coded as gravity bits, 1 bit per particle spin information. That distant gravity is then projected locally as needed, which causes the cosmic horizon to shrink. So Max now going to measure the entire sequence of an entangled pair, but this time from the relative holographic horizon. A feat we can't do, a feat nobody can do except for Max. When A can't translate its spin to B because A and B are different spatial addresses, yet have the same quantum address, then A's unused wave function encodes as a bit of gravity across the entire surface as an expression of causal uncertainty, which then makes A and B local. It brings their elements together so A's spin can properly affect B's spin. So the gravity bit allows each holographic element of A to interact with each holographic element of B across the horizon. Once that connection is made, the uncertainty is resolved, then the gravity bit is re-encoded as spin, and B will have the opposite spin of A. Max now sees the wormhole only appears to connect two distant points in space because the entangled particles are physically right next to each other on the holographic horizon. Holographic encoding from an information-dense distant horizon provides the structure necessary for spooky action at a distance. And here you can see, at our cosmic holographic event horizon, we see that our Landauer limit energy is 1.338 times 10 to the negative 53 joules. But its curvature is 1.3 times 10 to the 23 orders of magnitude greater. And that magnifies down to the 1 kilometer black hole by this order of magnitude to yield 1.74 times 10 to the negative 30 joules of gravity. It's really amazing how all of the energy in the horizon actually projects down to the local surface based on the curvature of the local surface. So now we can come up with an entropy formula for the entire universe through our discovery of gravity. And it's going to be delta entropy cosmic plus delta entropy local equals 0. Entropy actually conserves. Entropy does not continually go up over time. So this time we're going to use the entropy for gravity on the cosmic event horizon. We have delta S cosmic plus 1 plus delta S local minus 1 equals 0. As a local particle is close to crossing a cosmic event horizon, its spin information is redshifted, which shows as a reduction in energy, or S local is minus 1. The redshift increases until it becomes infinite, and the apparent spin energy appears to be 0. The cosmic horizon encodes the redshifted energy as the bit of negative energy on that horizon, which expands the cosmic horizon by 1 bit. Energy appears to be 0 locally from our perspective because of the extreme redshift. So the cosmic holographic horizon encodes the entire amount of that redshifted energy as negative energy because we see nothing, yet it still exists. That makes it negative. Now the horizon has negative energy bits ready to emit gravity locally to resolve entangled matter particle spin measurement. And here we have the entropy for local gravity. We have entropy cosmic minus 1 plus a change in local entropy plus 1. The cosmic horizon erases one Planck area minus 1 to correlate A and B's spin. It expends that gravity bit to make A and B briefly local. And by expending that bit, it breaks entanglement from that bit from the cosmic horizon. So now the gravity snaps back and emerges locally. And B's measurement emits one Hawking photon to conserve the total energy of the now slightly smaller universe. Think of the Hawking photon as a receipt for the erased Planck area. Proof that a gravity mission has occurred. So you could see in both cases, entropy conserves. I have some more information here for you. You can go ahead and peruse at your convenience. I want to thank you for embarking on this discovery journey with me. I hope you feel the sense of awe of how this just popped out. It just all came from answering that question that every time I've asked it, it was always the amount of energy in a constrained degree of freedom is too low. You can't do anything with it. Well, my friend said he thought that was weird, and I agreed, and I thought he deserved a better answer. So I actually chased it down. And I found how gravity emerged, not by looking for gravity, but just trying to answer this question. So sometimes you can see how you can find discoveries by many different methods. Sometimes it's not by directly looking for something. Sometimes you find things just by following a line of inquiry. Well, thank you so much for joining us on this discovery. Now you also are a part of this discovery. Have a great day.